Welcome back, ladies and gentlemen. In this video, we are looking at Newton's second law and bringing it up right away here in the beginning, by name anyway, because it's just too darn important. Continuing our look at Newton's three laws of motion, there really are four, but no one ever talks about them as being a set of four. It's the three laws. So anyway, here's second law. So why look at this? There is a huge amount of knowledge that comes from understanding of Newton's second law of motion. Huge amount. And you'll see it's relatable throughout a lot of the things we study in this class. Also, it basically is an equation, a very simple equation, but many people argue it is one of the most important concepts or equations in all of physics. Not that it is terribly advanced, but its importance comes from how foundational it is to so many other bits of our understanding of the way the universe works. All right, so recall about forces. What do we remember? A force is a push or a pull. Forces are vectors. That means they have magnitude and direction. Magnitude just means size, like the strength of the force. There are many kinds. They fall into two categories: contact forces or field forces. Forces cause accelerations. Specifically, an unbalanced force will cause an acceleration, right? Remember that. There can be balanced or unbalanced forces, and when they're balanced, you have equilibrium, and if it's unbalanced, you have, well, not equilibrium, you have acceleration. Okay, so there's this new idea that I want to throw at you called the net force, and it has nothing to do with like butterfly nets or fish nets or anything like that. Net is just the overall result or the overall effect when you combine things. You get a paycheck, and on your pay stub there's two important numbers, well, several others usually also, but you want to pay attention to what's called your gross pay and your net pay. Your gross pay is what you get before any deductions are taken out of your money, and your net pay is what's left over after all of the deductions are taken out, deductions for taxes or for medical insurance or various other types of things that might be deducted from your paycheck before you get your hands on your money. So net is the overall effect. And what does it mean? The sum of all forces acting on an object is how you find it, all right? So we use this symbol F net, and it's a real important thing. You want to get comfortable with that, the subscript net. And that just equals the sum of all of the forces. And I'm keeping this really simple right now. We could talk about further detail, like breaking it up into the x direction and the y direction separately. We'll get to that. But this symbol looks like a weird capital E. It's not. It's a sigma, and it means the sum of things. And when you have the sum, you're just adding things together, literally just adding. So for example, you have two forces both acting to the right, or at least in the same direction, and you add them together, you get the equivalent of a force that is as strong as the two of those put together, as long as they're acting in the same direction. Two forces acting in the opposite direction, if they're the same size, same magnitude of force, acting in the opposite directions, you add them together and you get zero. They cancel each other out. That would be the net, or the net force, if those were the two forces. So what if you have a force in the y direction and a force in the x direction, and you add them together, y direction, x direction? You don't get cancellation, and it doesn't exactly add up like 2 plus 2 equals 4. If they were each a magnitude 2, the answer, the resultant force here, the net force, would not equal 4. We have to involve a little bit of trig, the right triangle kind of stuff. Pythagorean theorem comes into play as well, and we could find out, well, that would be bigger than 2 but less than 4. And we could do math to figure it out. That's not what this video is about, though. Just giving you the general idea of what net force is. It's the result of adding things together. Okay, so what have physicists figured out, and it's been confirmed innumerable times. It's a very easy thing to look at, usually. How are acceleration and net force related? Well, the larger the net force, the larger the acceleration. And so we can say that acceleration is directly proportional to the net force. As the net force gets larger, the acceleration also gets larger. And by the way, they're happening in the same direction as well. And what about acceleration and mass? Imagine a shopping cart in the store, and when the shopping cart is empty, it's relatively easy to push, and it's also relatively easy to turn it and get it to change its direction. But once you have it loaded up with a billion cans of stuff, and those 500-pound bags of dog food, and well, there's a lot more mass in that cart, and suddenly it's not so you can't produce the same acceleration. It's harder to turn, it's harder to speed up, it's harder to slow down. So what we see is that larger mass is harder to accelerate, so acceleration is directly proportional to the inverse of the mass. This is 1 divided by the mass. And so, basically we've taken mass and taken the inverse of it. And so as the mass gets larger, well, that's the denominator of the fraction getting larger, and that means the overall value gets smaller and the acceleration will get smaller. Larger mass typically leads to smaller acceleration. Anyone involved in any kind of racing, automobile racing, but it even translates down to, say, a foot race, track and field, cross country. You're not going to want to race in big, heavy, massive shoes because they're harder to accelerate. It's harder to deal with. Race cars, you want them as light as you can make them, and lots of design and material science has gone into doing that. So anyway, what happens is, getting back to Newton's second law here, let's stay focused. Acceleration we see is directly proportional to the net force, and it's inversely proportional to the mass, or you could say proportional to the inverse of mass. Either phrasing is fine. And you put those together, and that is Newton's second law of motion. The acceleration is equal to net force divided by the mass. It's not usually presented this way, although this is usually the most the handiest form of the equation. It's actually usually presented F net equals mass times acceleration. We just multiply both sides by mass, cancels out here, and you got this. F equals ma. You may have seen that before. It is a very important equation. It kind of looks simple, but remember, pay attention to detail. As some of your teachers would say, attend to precision. There's lots of meaning here. For example, that's typically not a single force. That's the net force. That's the combination when you add 2 or more other forces together. Remember that. But the acceleration is the actual acceleration of the object. Okay, that is Newton's second law. We're going to use that one a ton. Thanks for watching. I'll catch you next time.